Hello, everyone, and welcome to the very last session of the season 10 of on VSA Online. Really cool that we made it 5 years, and I'm very happy to host Danilo Comminiello from Sapienza University of Rome, and he will give a talk on hypercomplex. I should probably warn you immediately that it won't be directly about hyperdimensional computing, but I believe it can be uh, kind of relevant, and I hope for a good discussion. So, without any further delay, Danilo, the floor is yours.
Thank you so much. Thank you so much, Jenny, for your introduction. As Jenny said, I'm going to introduce the world of hypercomplex. Despite the word hypercomplex, the field can be even very easy to be managed. So in this talk, I would like to explain how to deal with something that extends the complex value domain and how we can build these hypercomplex theory algebras in particular in order to build very efficient and effective deep learning algorithms, neural networks, but in general, any kind of learning algorithms that can be exploited in the real domain for certain specific types of signals. Okay, so for different applications. So first of all, I will give an introduction before starting, I would like to say that this talk is based on journal magazine that we published together with Eleonora Grassucci and Aurelio Uncini from my university and Danilo Mandic from Imperial College London. So I will give you an introduction to hypercomplex algebra, just a quick introduction, just to say, just to know what we are talking about. I will explain how to build learning systems in the hypercomplex domain. Uh, then we go a little bit into the details, how to exploit some properties of hypercomplex learning, and in particular some correlations that we can have. And then we show how to leverage this inductive bias, or a set of properties coming from the algebra, in order to build some neural networks that can be very powerful. We also see how to go beyond hypercomplex algebra and how to generalize for lots of signals and scenarios and applications. And finally, we'll give some application examples using hypercomplex models. So let's start. Please feel free to stop me whenever you want and ask me a question, of course. We start with hypercomplex algebra. So why we need hypercomplex algebra? So actually nowadays we are working on a lot of multidimensional data. So actually the focus is to work with multi-channel audio, so with uh, data, video, images, colored images, LiDAR data, and also sensor data fused together. So when we work with this kind of multidimensional data, we need to deal with complex structures and relations. Also, we need some kind of optimization of geometrical properties, because when we have multidimensional data, probably we have some kind of geometry, some relations between the entities in the data. And also, of course, we need to deal with the huge complexity of large-scale neural networks. So you are very expert in this field, how to deal the complexity of networks. Today, I would like to give you a different perspective, so that can be also, of course, associated to hyperdimensional data methods, but actually we want to exploit the hypercomplex algebra in order to save some kind of computations from a software point of view. So why do we need hypercomplex models? So hypercomplex is not something very recent, and their origin comes from the last century. And so, but of course, the first attempt to use hypercomplex method to multi-dimensional and multimodal data was, for example, for the representation of the character of Tomb Raider in computer graphics, and in particular for the rotation, because due to the properties that we will see of hypercomplex algebra, and in this case of quaternion algebra, we are able to represent some kind of movement like rotations in a more natural and smooth way. But we will focus later also on the reason why we talk about this. What are the advantages of hypercomplex domain? So why we focus on hypercomplex domain? First of all, because we can process the data in the domain they reside. So there is no need to focus on processing channel by channel, or making some kind of architecture and then fuse the information, or having some kind of very complex structure. So we can actually use the data in their very domain, and we can process the data as they appear. Hypercomplex domain is very, very useful because we can exploit the multidimensionality and the high correlated nature of the input signals. So they are very, so hypercomplex models are very useful, especially when we have a strong correlation of signals. But of course, in general, when we deal with multidimensional or multimodal data, very often we can find some correlations. Also, we can redefine neural computations, and this is very important because redefining some operations with the help of hypercomplex algebra, we can exploit, we can we can reach a significant reduction of network parameters. So hypercomplex model capture spatial relationships and intricate patterns. This means that actually we can combine different details both in the during the spatial processing, but also on the time domain, as we will see. The nice thing of hypercomplex model is that we can apply to a different variety of application and process a lot of data, and at the end we will show how we can move from the processing of audio signals to images, and also other kind of examples, also computer graphics and lots of different things. But let's come back to the origin of the terminology. So what is an hypercomplex number? So hypercomplex number denotes an element of a finite dimensional unitary algebra, but not necessarily associative or commutative over the field of real numbers. So actually, it is a kind of extension of real and complex valued numbers, but with different properties. So we may have hypercomplex algebras with different properties than associativity or commutativity. So hypercomplex number denotes a family of number systems that extend the complex value domain. So actually, instead of having just one imaginary unit, we can have two, three, or even infinite imaginary units. So hypercomplex algebra was introduced in the late 19th century. So it is at the base of the group representation theory. And actually it comes from what is defined as the Clifford and the Cayley-Dickson algebra. Especially from the Cayley-Dickson algebra, we can find some good initial properties from the algebra. This is due to the fact that we can relate the dimensionality, the input dimensionality, to the dimensionality order that is related to the property of the Cayley-Dickson algebra. So actually, we can say that we can have the dimensionality order that can be defined as a power of 2 of m. So with m is any number, so integer number. So actually moving the order of m, so moving from 1, 2, 3, 4, we can derive the dimensionality of the hypercomplex algebra. So if we use 1, m equals to 1, we can, of course, derive the complex valuing domain that we all very well know. If we use m equal to 2, actually we have n equal to 2 to the 2, so we have n equal to 4. And for n equal to 4, we can have other hypercomplex algebras like quaternion algebras or tesserae, or even other hypercomplex algebras. Then for and so on. So if we have m equals to 3, we can have the dimensionality order of 8, and so we can define the octonion algebra, then the sedonions, and so on. So actually, we have this kind of composition. So hypercomplex algebra is a large container of all these of specific algebras, each of which can have their own properties. Okay. But let's focus on some multidimensional signals. So what is the connection between hypercomplex numbers and hypercomplex signals? Okay, so we can okay, there is a question, maybe I can answer here. So the question is, when you move from real numbers to the complex number, one thing you gain is the algebraic closure, and one thing you lose is the total order. There are some similar trade-off. Of course, there are some trade-off, and the gain of so the connection between the algebraic properties and the things you will lose is also some kind of practical things you can lose will be very evident, and I will show you some examples also later with real applications. But it is very interesting because you can understand where you can use these algebras and how you can exploit the maximum flexibility from these algebras. So actually, we can represent a multidimensional signal. So when I talk about multidimensional signal, you can think of a multidimensional, multi-channel, or multi-views, anything which is composed of different channels or dimensionality, okay? So not just a one-dimensional signal, but signals or even a composition of signals. So imagine that you have a multidimensional input signal. Instead of just representing each channel separately, we can group together in a hypercomplex input signal where you can associate each channel to uh, a real valued component of an imaginary unit. So of course you will have the real part like in complex number, then you have imaginary units. And so you can think that you can cast your signals in each dimensionality, in each imaginary unit, but also the real part. So, of course, if n is equal to 1, this is just a real valued signal, and this means that we have just one dimensionality. If the real component is 0, we can have, it is called a pure hypercomplex signal. So this means that we have only imaginary units with 0 real part. So what are the algebraic properties that we need to take into account? Of course, when we grow with the order, we need to consider that we may lose some kind of properties. Okay, so actually we have some closed form, but we lose some properties. So for instance, when we use m that is larger than 2, we have hypercomplex algebra of order 4. These kind of algebras are non-commutative. So this means that if we take the square of each imaginary part, we have that the square is -1. But also, if we grow with the dimensionality, we can lose associativity. Then for n equal to 16, we have zero divisors. So actually, every time the order increases, we lose an algebraic symmetry. And this is very important because we need to reach a trade-off between what we gain and what we, of course, lose. Okay, so one of the most popular hypercomplex algebra, of course, is the algebra with order equal to 4. That is known as quaternion algebra. So quaternion algebra was invented by Sir William Rowan Hamilton, and there is also a stone in a bridge of in a suburb of Dublin in which says here as we walk by on 6th October in the 18th century, Sir William Rowan Hamilton, in a flash of genius, discovered the fundamental formula of quaternion multiplication, in which we don't have the commutativity. Okay, so this is something that was cut in a stone. And so actually, Sir Hamilton worked a lot on this topic, and he was kind of obsessed by these algebras. So he said every morning in the early part of the both-sided month, on my coming down to breakfast, your little brother William, Edwin, and yourself used to ask me, "Well, Papa, can you multiply triplets?" This is a sentence Hamilton said to his son. So, well, Papa, can you multiply triplets? And he said, with a sad shake of head, no, I can only add or subtract them. So actually, it was something that was very, very. So he was obsessed by this fact. So he studied a lot. But of course, we can have some kind of results from the study of Hamilton, and actually we can exploit the study of Hamilton. And so how to build quaternion representation for multidimensional signal. So actually, in a quaternion, we have one real component and three imaginary units, okay? So actually, we can represent four-dimensional signals, just casting each one of the channels in one imaginary component, um, or even considering a pure quaternion and working with 3D signals. Okay, so this is very important because you can manage 3D signals or 4D signals just as a single quaternion entities. So quaternions are characterized by non-commutativity properties. So actually, as said before, if we take the square of each axis, the result is -1. But also, if we multiply the axis and we take the opposite as the minus sign. Okay, so I times j is equal to -j times I, and so on. So this holds for all the multiplication from different axes. So given these very few properties, we can redefine, so not with, but of course Hamilton redefined the operation of the multiplication. So actually, since we have a non-commutativity problem properties under the operation of vector multiplication, we can write the product between two quaternions in this way. So actually we have the first quaternion and the second quaternion, and so we can have element by element the multiplication. Considering these non-commutativity properties, we can have a kind of representation that actually is also represented by this multiplication table, and where you can see that on the main diagonal, you can have one just for the multiplication of the square of the real part. So the square of the real part is as it is, so as it works in the real domain. But as long as we consider imaginary units, the square is equal to -1. And also we can see that we lose symmetry. So actually, if we have the multiplication ij is equal to k, and j times I is equal to -k. Okay, so we have this loss of symmetry. So this redefinition of the product is known as the Hamilton product. So I don't want to boring you so much with the other complex algebra, but I think it is very interesting to understand how to move from some mathematical properties to very powerful and also large-scale neural networks. Also, it is very important to exploit these, apart from the mathematical point of view, the hypercomplex algebra has also a lot of geometric properties, and especially rotations are very, very interesting because actually we can exploit the redefinition of this multiplication to create some rotation just as a chain of multiplications. Actually, it is very interesting to look into the mathematical and geometrical properties of rotation and how rotation can be achieved by composition of multiplication, because actually it is very, very interesting to have a multiplication that can solve some ambiguity, like the gimbal lock, that is something which is very, very well known in aeronautics, and so the study of movement of planes and so on. Also, another property is the quaternion involution. So the involution is a kind of mapping of a quaternion for its inverse of self-inverse mapping. So it is a kind of geometrical properties, but it is very, very important because we can deal, so we can explore some kind of, we can understand some kind of correlations between vectors and so signals in the quaternion domain. Okay, so I hope so. I didn't go too much into details of the algebra, but I would like just to give a rough overview about the main properties of the algebra, the hypercomplex algebra. Now we can make another step ahead and see how to exploit these very few algebraic and geometrical properties to build a learning system. Okay, so hypercomplex deep learning allows to reduce the number of parameters by sharing blocks of parameters according to vector multiplication rules. So actually, starting from exploiting the redefinition of the multiplication of operation, we can think of reducing the number of learnable parameters in a learning systems like in a learning system like an adaptive filter rather than a neural network or even a large-scale deep learning model. So in particular, neural networks and hypercomplex neural networks, so neural networks defined in the hypercomplex domain may process signal channels as a single entity. And given the properties of hypercomplex algebra, we are able to grasp some kind of internal latent information. Okay, so something that is unknown from an a priori perspective. And we can also preserve some kind of intra-channel relations. This is possible due to the algebraic multiplication properties and how to redefine operations. So this is a kind of workflow of hypercomplex deep learning. So actually, we may start with input signals, any kind of data that we have in the real domain. Okay, so we are in the real domain. And we can have multiple signals that come from a multi-sensor system or any kind of multidimensional data. Then exactly like we can do for the real value domain, we just separate the channels or the dimensionality. So actually we split the channels. So imagine that you have multiple sensors, you have one signal for each sensor, okay? Then this is something that you can do even using classical real value domain models. Then we can move to the hypercomplex domain. So actually, we may represent these signals in the hypercomplex domain. We can have a compact representation, or we can represent the signals as they are, but using a hypercomplex algebra. So actually embedding and casting the channels into a hypercomplex signal. Once we have this signal, we can process this signal using hypercomplex deep learning models. So those models in which the operations are redefined based on the hypercomplex algebra. The interesting part is that once we have the output is again something on the real value domain. So we don't need to do a lot of different things from the input-output, but actually it is sufficient to work on the models. Okay, so working on the models is sufficient to make some kind of good improvement of our process. Let's see how to define learning rules in the hypercomplex domain. So we may have relational rules, especially related to the product between two hypercomplex numbers. These relational rules can affect the definition of the learning operation. Then learning layers are usually defined as elements of the hypercomplex domain. And actually, based on these domain rules, we can redefine some operations like multiplication, convolutions, attention, and all the kind of operation that we can have in neural networks. So these are a kind of table representing the domain-specific algebra definition. So we have real domain, real valued domain, complex valued domain, in which we have all the properties. We have the quaternion in which we lose the commutativity, and also then we can have also dual quaternion is an extension of quaternion, but octonions, in octonions you lose also associativity and so on, okay? You can note that each time you grow, you have a different table, multiplication table, okay? So actually, if you consider the weight, the learnable parameters, you can represent the learnable parameters using the multiplication table that is related to the specific algebraic description. How to deal with how we can exploit this fact in the operations to build the neural networks. Of course, we can build hypercomplex, fully connected or convolutional layers. So just redefining the operation. So imagine that here we have a multiplication, but instead of having a real valued multiplication, we can have quaternion multiplication rather than octonion multiplication and so on. Okay, using just exploiting these operations. Then for activation functions, since we need some nonlinear functions that are also differentiable, we can use some split activation function in order to keep something well contained, because it is an approximation, but it is a very soft approximation. But also you can use, like in neural networks, convolutional layers, batch minimization and pooling, and so on. So I would like to say how to build fully connected layers and what is the benefit of having this representation, just exploiting the Hamilton product. Okay, so if we want to build a fully connected layer, we just have a weight matrix and a quaternion input vector. We can just consider this very simple example in which we have the weight vector in this case. So the weight matrix in this case is composed of 4 elements, and the input signal is a quaternion signal, for instance, in which we have 4 components cast in the 4 components of the quaternion. So we need to make this kind of multiplication. So we start from the definition of the real value domain. So how to implement this equation in the real value domain? So actually in the real value domain, we have a matrix in which we have 4 times 4 parameters that we need to learn using backpropagation and so on. Okay, and we make some kind of multiplication with the input signal. Okay, so at the end we have 16 different parameters. When we use a convolutional quaternion valued fully connected layers, actually we can implement, instead of having 16 different parameters, we have only 4 different parameters. And actually we can reuse the parameters in order to build the composition of the quaternion matrix as it appears in this table. Okay, so actually we can learn only 4 different parameters and then compose, based on these learned parameters, we can compose the quaternion valued weight matrix. Okay, so this means that instead of learning 16 different parameters, we are just learning 4 different parameters. Okay, so we have a reduction of 1/4 of the overall number of the parameters, and this is a very huge uh, saving of the parameters, because actually this is a very simple example. But imagine that you have, instead of 16 parameters, you have millions of parameters like the modern architectures. And so you are able to reduce of 1/4 the number of parameters. This is a very huge saving. And another thing is that, as we will see later, this number is related to the order of the hypercomplex algebra. So in this case, we have 1/4 of the reduction, due to the fact that we are using of a hypercomplex algebra of the 4th order, so the quaternion value. But if we use even a high order hypercomplex algebra, we can achieve even a higher reduction, okay, of the parameters. Of course, we need to, there are some compromises, and so we need to find a good trade-off between performances and reduction of the parameters. Of course, with the same structure, we can compute the quaternion, the gradients, so how to learn the parameters. There are different theories, and also algorithms. There is some kind of pseudo-gradient approximation, which is more easy to be computed, or also you can have some more complex gradient operation defined in the quaternion domain. Of course, there are a lot of very, very interesting studies on that part. This is another representation of a quaternion fully connected layer. So instead of having all the connections that are the same, actually we have the connection that has that have the same way. So we have a reuse of the ways that we learn. With the same approach, we can redefine attention layers, also convolutional layers, graph convolutional layers, and so on. So because starting from the Hamilton product, we can redefine also the other kind of layers, which are based on multiplications or convolution. So actually, we can just, given a kind of redefinition of the operation, we can implement a lot of layers. So based on this, we can see very quickly so how to exploit some correlation. So apart from, I don't go into details of quaternion statistics, but of course, we can study the statistics and the correlations directly in the quaternion domains. But given all the mathematical and statistical theories, actually, we can say that the channels, the definition of the layers of a neural network in the hypercomplex domain can help to capture interchannel and intrachannel correlation better than real-valued networks. So actually, intrachannel correlations are related to the relationships between the same channel across different layers of the networks. Okay, so actually it is like a process of each signal, so each signal for each channel. And so we can have some kind of intra-channel correlation help to grasp global features. Okay, so it is like having a low-pass filter highlighting some important characteristics of the input signals, like shapes, curvatures, and so on. So it is like having a low-pass filter for each signal. But we can also pay attention to inter-channel correlations. So those correlations which are in common with our so local features that can be found into different channels and are very difficult to be captured by real valued models or fusion architectures and so on. So it is like having a kind of high pass filter for the channels, and we can have lower local features that can results in increasing the representation, the level, the quality of the representation. So it is like having for each channel we can derive some kind of low pass or intra-channel correlations, but also inter-channel correlation, which are more detailed, so like high frequency detailed information. So based on this fact, we can exploit this correlation as it is an inductive bias. So as it is something to be exploited from the point of view of the neural network. And so we can build neural networks that can exploit this presence of correlations that is highlighted by hypercomplex models. So based on this, we can think of different inductive bias. So actually what is inductive bias, I said, is just a set of theoretical assumptions that can provide, that can be used to develop neural networks in a certain way. And so actually we can have some kind of relational and non-relational inductive bias. We can have inductive bias in different neural networks like convolutional networks, recurrent networks, and graph neural networks. Also, there are non-relational inductive bias that are related to some kind of regularization approaches. Actually, we can focus on some bias that are focused on the dimensionality of the signals. So the dimensionality matters in this case. So algebraic bias also is something that we can exploit, as well as geometric properties, and also some invariance and equivariant biases and some regularization bias. So actually, for instance, the dimensionality bias is very important because, as said before, if we increase the dimensionality, we can have some larger representation of the signal, but also a significant reduction of the parameters. So, for instance, we can every kind of multidimensional signal can be, it is good to, so how to exploit dimensionality bias just using some signal that is multidimensional by nature, by definition. We can exploit some algebraic bias, which are very specific for the hypercomplex algebra that we use. So distributive, associative, commutative, and so on. So these are related to the kind of order and also the algebra that we use. Also, we have, of course, some benefits and challenges, of course, because we lose some properties, and so we need to understand how we can lose some properties. We may have some geometric bias exploiting, for instance, rotations, involutions, something which is defined for the specific geometric, for the specific hypercomplex algebra. And also it is very interesting because we can have we can make some kind of spatial transformation very easily using quaternion. So for instance, using quaternion domain, we can have rotations very easily and without any kind of artifacts that we may have in the real value domain. But also we may have some kind of 6 degrees of freedom in the sense that we can also perform rotation and translation in the same way. So just with a few operations, and so implementing a dual quaternion, we can have very easily some kind of transformation of objects in the domain. So if we consider that each signal can be seen as a vector in a space, it is very easy to understand that how powerful that can be, these kind of geometrical properties. Also, we can have some kind of other properties like invariance biases or equivariance bias. So, for instance, we can have models that are rotation or translation equivariant. How to prove that? So imagine that we have a chaotic system and we want to translate the system, but also translate and rotate. Okay, so while the original system may be some kind very so easy to be tracked, when it is translated, it is a little bit more difficult for a real object, for a real method to track the translated system. So the red lines are for the real value for the model. When we have translation and rotation, of course, the model is not able to track anyway the model. While for quaternion, we can have some good rotation, some rotation, but at the end it is not good as well. When we have translation and rotation, for instance, with dual quaternions, we are able to track this kind of system, and this is very useful, and we will see in some examples. Also, we can apply regularization methods similarly to real valued problems. One of the drawbacks of the hypercomplex algebra is that, of course, we are very related to the order of the algebra, and the order is a power of 2. Okay, so actually we can move from 2 to 4, but we don't have 3. Okay, so we don't have 3, and so we don't have 5 as order. So actually, up to some years ago, we were limited from the fact that we could consider multidimensional data, but considering some specific dimensionality. But we can try to make some kind of approximation, try to lose some algebraic properties, but generalize over any dimensionality of the input. So for instance, one of the idea is to parameterize the hypercomplex domain. So actually we can decompose the matrix multiplication like considering a kind of Kronecker factorization. And so basically consider that we have a well-known algebra like the quaternion algebra. We can just decompose the 4 parameters and having the quaternion Kronecker product with these 4 matrices which define actually the algebra. Okay. So since we are able to make this kind of decomposition, actually these are the matrices that encode the algebra rules. But what happens if we let a neural network learn the algebra rule? So imagine that we don't have this knowledge and we want a neural network that is able to make this kind of 0 and 1 in the right way. So if we make this kind of operation, actually we are able also to consider any kind of number of elements of the matrix that compose the overall that compose these original matrices. So actually, we can generalize this kind of factorization with any number of order of the hypercomplex algebra, so leading to a reduction of 1 over n. So this is very, very powerful. So for instance, for a colored image, instead of considering a pure quaternion, that it means that we need to consider some additional operation, we can have some kind of processing in the domain of the colored image, like red, green, and blue. Okay, so in the three-dimensional space. So also, of course, we can save some parameters. So all with some properties. So basically, the main property that is exploited in this way is the Hamilton product. Okay, so it is a kind of decomposition of the Hamilton product. Okay, so we focused on the Hamilton product because it is the most relevant properties of hypercomplex algebra that can lead us to save a lot of parameters. Of course, we can lose some properties, especially some geometric bias in the parameterized hypercomplex. And actually, this is related to some experiments, for instance, when we have systems for rotation and translation. While dual quaternion is very able to track these systems with the parameterized hypercomplex network, we don't have these properties. Okay, so we need to try to have some balance. Of course, we may save some more parameters. We can have some good reduction and also good performances, but as long as we don't have to incur in some geometric properties. So if you need, for instance, some translation equivariant method, so it is better to use some well-closed algebra instead of using a parameterized algebra. But of course, it is a kind of trade-off that can also extend and generalize as much as possible these methods. I would like just to close this lecture to give this talk to give some overview about the application examples that we can have in using this kind of models. So, for instance, image analysis is maybe the most trivial application examples, because we have colored images, for instance, and we can have, of course, channels that are very, very correlated. And so we can use hypercomplex model for any image analysis, any deep learning models that can be used for image analysis. So, for instance, we used one of the first examples are for image classification, and actually we saw that even with very, very complex models and using some very large data set, we have a very huge reduction of the parameters. Also having some improvement of the classification accuracy. But of course, we can apply some like convolutional neural network models, but even some more complex deep learning algorithms, so deep learning models like generative models. Okay, so we can redefine generative models using the same approach. So, and it is very nice because we can extend to a wide variety of models, just reformulating and redefining the operations. So, for instance, there is some kind of image-to-image translation when we want to move from a source to another object, and so these are some kind of transformation, and with the parameterized hypercomplex model, we are able to grasp some kind of details that can be focused, that can be captured and also synthesized by the generative model in order to represent some details in a more accurate way. We also use the hypercomplex methods for 3D audio, for instance, for the first order ambisonic 3D audio signals. So in the ambisonic, the ambisonic is a microphone recording techniques in which we have one omnidirectional capsule and three other capsules that are the velocity that measures the velocity, while the omnidirectional capsule measures the pressure, the acoustic pressures. So actually, we can cast these microphones into a quaternion, like considering the real part and the imaginary units, and we can build in this way models which are very able to reproduce the spatial, the immersivity of the 3D audio. We can also use quaternions or hypercomplex in the embedding. So instead of just encapsulate signals as they are, we can consider some kind of compact, compressed representation of the signals. And so considering the quaternion, we can have some kind of quaternion embedded system that can be used for classification, for instance, in speech emotion recognition. Another very interesting application is for the analysis of multimodal and multi-view image, especially into the medical domain. So this is a very nice application because actually when we have, for instance, a problem of the breast cancer analysis, a physician so a doctor is used to look at four image altogether because we have two views for each breast, and so we have usually four images for each analysis. And so while a clinician is able to look at four images together and make some kind of diagnosis, if traditional deep learning models are used to process image by image, channels by channels, losing some kind of intrinsic correlation between the images. So actually, while it is very good to have some global relations like the shape of the object and so on, hypercomplex models are also very good in finding some local relations. So like some kind of high frequency details that can be that can be recognized by different modalities, okay, different views. And so basically we can build, we derive some kind of multi-view hypercomplex learning for breast cancer screening, just having some kind of view. We can have a larger view at patient level, so we can have the view of the four images together, and then we can even focus on of a breast level in order to say if there is a kind of diagnosis related to one breast or the other. And this is very important to have some explanation of how it works. So for instance, this is an example which is very clear because imagine that we have these images and on one breast you can see you can detect one mass of area of interest, and also in the other area you can see the same. You can see a different region. So if you use a real valued model, actually you will see something which is the best, so the most significant area of interest between the two. While if you use the hypercomplex model, you are able to visualize and detect all the areas of interest. And the same for the other examples. So it is very, very interesting because, of course, it can give some different perspective and also make very useful for this kind of application. And also considering a huge save of the parameters that we use. This also for instance, for computer graphics, for pose estimation, in which you can exploit some rotation and translation, and of course, for this kind of movements, the dual quaternion is more useful to uh, use some kind of equivariance properties in having some good performance. So to conclude, so why we do need to use hypercomplex model? Of course, because we can have a good improvement from the point of view of the effectiveness of the models related to the inductive bias that are intrinsic in the model that we developed. And at the same time, we have a significant reduction of the parameter up to 1 over n, with where n is the dimensionality that we use for that model. Also, we can have a very compact representation. We can perform transformation very easily in a high dimensional space. And of course, we can extend inductive bias in a lot of methods. So we can redefine a lot of deep learning methods using just some hypercomplex algebra properties. And of course, we can design a lot of hypercomplex neural networks for specific applications. Of course, there are a lot of possible work in this field, starting from building new models, exploiting some different algebraic properties, because I just showed you a very limited number of algebraic properties, but of course you can discover new properties and exploit those properties to create some new deep learning algorithms. And so it is a very, very interesting field of research. And of course, it would be very interesting also to think of one of the limitation, for instance, in this case, is that while we can reduce a lot of parameters from a software point of view, it would be very great to have some research from the hardware point of view, because from the hardware point of view, there is probably nothing in this field, and it will be very, very useful, because having these models implemented on edge devices or any kind of very smart devices, fast devices, will be very, very powerful for a lot of applications that can be used in real-time processing. So here you can find some of the references. So that's all from my side. But of course, if you have any question, I'm available.
Danilo, thank you very much for the great lecture. So let's open the floor for questions, at least for a few questions, because we kind of a little bit overshoot the
Yes.
time. But so let's see. Um, Yes, I had a couple of questions along the way you presented. One concerned about larger dimensionalities. So you somehow answered it yourself. So of the hypercomplex. Um, and then maybe kind of very small question on really mapping the channels to uh, components of the hypercomplex. Is it I mean, practically how would it?
Yeah, actually, it is very, very simple because we don't need to. So I forgot to include any link about the repository we have for these models, but actually, it's very, very simple to use these models because you just need to have data like they are and using matrices, tensors, or whatever to process those data, and just redefine the operation. So actually,
Mm,
we don't have operations like in the complex value domain, but we just redefine the operation in order to have real valued operations, like having just a redefinition of the operation using the multiplication table, and then have a real valued operation. So it is like a kind of mapping, but it is very, very easy and
mm,
fast to be applied. So we built this kind of repositories of code which actually, instead of having the multiplication, we have the Hamilton multiplication. And so you can use the operations in the same way. So you can have the same syntax for any kind of real valued algorithms, just using a different call for the operations, which
mm.
is defined in this way. But at the end is very, very easy.
But probably you can send me the link to the
Yeah, yeah, of course. I
repository
will.
offline so I can distribute it
Yeah, yeah, yeah. I will add
easily
to these
to those
slides. Yeah,
interested.
yeah, yeah.
All right. So let's see if we have more questions given the time.
There is
Tony,
Yeah,
please.
yeah. I had one question. So it's fascinating stuff. I'm trying to map it to something more familiar to me so I can understand it better. And so what you're talking, it's like each okay here. So if we think about like image data where we might have colors, so
Yeah,
like RGB, alpha, and traditionally when representing that with real numbers, each pixel could have four real numbers, and then we have, like we might have an image is 1,000 by 1,000, and it's represented as four sort of independent channels, and then we process that all using real matrix algebra in convolutional neural nets or whatever. So is what you're saying is that, like, for each pixel we would have, you could, I don't know whether this is useful for color, but the different attributes of that pixel become more tightly bound together in something like a quaternion, and
yeah. It
and
is
then
very interesting because so actually the diff so um, the um, the important, the interesting facts happen not in the not at a pixel level, but in the propagation of the neural network computation. So when you learn the representation of pixels or composition of pixels, so when the neural network propagates layer by layer, also it learns the relations between the channels. Okay, so not only the relations pixel by pixel, but even in different areas. And so it is very interesting because actually, if you have some image processing transformation, you can have some very small advantages because you are just operating at a low level processing, so a low processing level. But if you are using a very large network, this means that this kind of relations are propagating inside the network at different kind of representation. So you can have a low-level representation like very small features, so very simple features, but also at a abstract level, which it is a composition of some object in the image at a most large view. So it is very interesting because you can propagate this kind of correlation inside the network. And as long as you use large network with a lot of parameters, you can have more a huge impact in the performance because you are saving more parameters, and you can also also have some models that are more regularized, and all the parameters are focused on some specific tasks. So it is a very nice combination of a lot of things. So the fact that you can save the parameter, but also reducing some parameters in an optimized way. Reducing the parameters in an optimized way it is like having some kind of pruning of parameters that are not useful for your goal, and so you can have also some kind of improvement from the performance. So it is very fascinating in this way because actually you have some kind of correlation not only at a pixel level but also in the propagation of the representation of the pixels in the different layers of a network that we can have.
We have one question from, I guess, Ross. He was unmuted, but now he was off. And then we have a question from Josh, and then we try to.
Yeah, of course.
Actually, I would also have a question.
Yes, please. Yeah, and then Fritz, of course. Yes, absolutely.
Okay,
Thank
so
you.
I was just this is a two-part. It's a continuation of what Evgeny was asking, what Tony was asking, I think. So I mean, it seems to me that where you get value from this is when you're matching the algebraic properties of the neural network to the algebraic properties of the latent entities in your inputs. And so the question is about the mapping of the inputs into this hypercomplex basis. So the two-part is the simpler part of the two-part is taking Tony's example. If you had a single pixel in a color image where you're mapping alpha, R, G, and B to the four components of, say, a quaternion.
Okay.
Are all the four components equivalent? So it really doesn't matter which, whether the alpha gets mapped to the real component, the I, the J, or the K. So that's part one of the question. Part two then is sort of then taking that to a bigger level. If you're looking at a whole image, would things go horribly wrong if what you did was you mapped alpha of one pixel at one corner of the image to the real component, red of a pixel from another corner of the image to the I component of the same quaternion, and so on. So basically, does how you do the mapping from the input space into the quaternions make a difference?
Yeah. So this is, of course, the power of neural networks in the sense that since we are using learnable parameters, it is the network itself that learn what is the part of the image which is correlated to another part and so on. So probably you will weight some more significance when you find some good correlation or less significant and so on. So depending on the network. So when the network is trained to some tasks, of course, you have those weights, and those weights are learned from the neural network that is also able to make this kind of association in a good way. So the part is that we actually have the input signal. So in the embedding part, actually we can have the input signal. We can build this input like imagine that we have 4 signals, or imagine that we have a matrix, a colored image. So you have three matrices. So you have a tensor of 3 matrices in the real value domain. You can build also another tensor in which you have the weights for each of the weight matrix. What is so this part? Consider that this part. So in this example, which you have the input, which is a vector, and the weight matrix, which is a matrix. Actually, you have a real valued here and real valued here. What is different is that you have this operation, which is defined based on the multiplication table coming from the algebraic property. So basically, we are learning these 4 components, W0, W1, W2, and W3, and then just resembling this matrix. So actually, the processing, the input, the processing of the input is very, very simple, because it is like having a classic real valued operation. So the only thing we need to pay attention is to, of course, redefine this operation based on the multiplication table. This means that instead of having just 16 free parameters, we have only 4 parameters. And then we need to, once we learn these parameters, the forward process is built by having this matrix in which we have these parameters resembled. Of course, step by step, the network is learning how to give some good association, so how to have some good numbers to these parameters in order to exploit at maximum at best the association between parts of the pixels or parts of the images or the data in general. I don't know if I answered to all the.
I think the idea is clear. So let me hand over to first chat, a quick comment. So what you get or lose when you trade commutativity or associativity?
Okay, so when you lose commutativity or associativity, the fact is that, of course, you cannot consider the multiplication as it is, but you need to do this kind of further steps. So you need to redefine the multiplication, and so you need to resemble the multiplication table according to the properties. Okay, so this is the reason. So actually, is the reason why we have this matrix composed in this way, because we are losing in this way. We are losing commutativity, and also here we lose also associativity, and so we have a larger matrix here. So if you don't have this loss of commutativity, of course, there is no need to resemble this multiplication in this way, and so you can proceed with a classic classic approach. Of course, this is a kind of bias. Okay, so this is a kind of for what concerns the multiplication. You can have only, I don't know, the four parameters resemble even randomly. Okay, so you can have even random resemble. You can just use some kind of reduction from the Hamilton product. But if you do this composition in this way, you are forcing this object to be a quaternion. And so so a part of having this reduction in the multiplication, you have the other properties like the rotation, translation, and so on. Okay, so you are giving a bias towards quaternion. So this is the way why it is important to follow that rule.
Okay.
If you don't follow that rule, you can have the parameterized, which is more free, but of course, you may lose some properties like translation, for instance.
Thank you, Daniel. And then, so Fritz, please.
Okay, so given the time, I will make it short, and my camera doesn't work.
It's okay.
Thank you for the talk. Very interesting. I think my question has been answered, but I will definitely look at your papers, Danilo. Thank you so much.
All right. But listen, I think I'm very happy. I'm happy for the discussion, and I'm very happy for the talk. And so, Danilo, thank you very much for the great talk once again. And thank you all for attending this last session and being disciplined and attended all previous sessions. So by this, I conclude season 10 on VSA Online, and see you in September sometimes. So I will announce the first session within some short time. So and propose a program. Okay, thank you.
Evgeny and Dennis
again
need
for
a real
invitation.
thank you for running this thing.
Thank you all.